So let's start with some questions. In the interpreter pattern, how many times can I use that abstract syntax tree to evaluate an expression? Yeah, as many times as you want, right? Second question is, why would you want to do it more than once? Yeah, some values can change, right? Again, we have got maybe constants, they don't change. The operations don't change, but there could be variables, and those variables could change values, right? So any questions? What's that? Must be too easy, right? I'll have to work on harder assignments then, right? Or it could be the assignment is to do it too far away, right? There are some tricky parts to assignments, so you want to be thinking about them. Well, years ago, I had a student take this class who was a lawyer, um, which is sort of odd, but he was becoming a patent lawyer, and you need so many technical credits to become a patent lawyer, and so this is one of those technical part of that requirement. Um, but of course, being a lawyer, he was very verbally gifted, and he would then come up with these great names for various patterns and groups of patterns. And we're about to talk about today two of the patterns he would mush together with several others for reasons you'll shortly see. The strategy and the state patterns. Talked about this last time. So the strategy pattern, again, one of the two design principles that the Gang of Four talk about, one of them is favored composition over inheritance. It's like most instructors, I create a fake example to motivate the whole thing. What if I have an ordered list, right? But there are times when I want to order differently. So I want to order, sorted, reverse sorted, or random, or we could also just do it order in which things were inserted, right? So a bunch of different ways in which we may want to order that list. And then you say, well, we'll just create subclasses, right? So we'll create a subclass for sorted list and a reverse sorted list and a list that doesn't change order, just how you add them. After all, inheritance is one of the big things of object-oriented programming, right? So here's an example of inheritance. But the problem is, yeah, one tool doesn't fit everything. So what happens when we got orthogonal features, right? So different orders, and then, we need to worry about threads, right? So we may want a synchronized version of these so that when we have they're used within threads, right? You don't have to worry about the threading issues. But there's some overhead for doing that. So we also want unsynchronized versions. So when we know this list is not going to be used in a threaded environment, we don't have to pay that overhead, right? And we may want a mutable version of these things and an unmutable version, right? Having unmutable data or non-mutable data is very popular. Why? Because it's safer, right? Now, if we're going to use inheritance to solve, get all these options, what do we get to do? Well, we get to do that, right? And that's clearly not going to happen, right? I mean, it's clearly nonsense. And also, we want to be flexible, right? We may want to start off with an order list that's sorted, and then realize, we make it synchronized. So how do we do that, right? In this case, make it random. How do we change our behavior at runtime? If we just using inheritance, we can't do that, right? If we rely on inheritance, inheritance is a compile time feature, right? It's fixed at compile time. So the answer, of course, is we want to be able to configure objects at runtime. And so the basic idea behind the strategy pattern is, there's some object, some class, which they, in the abstract we call the algorithm, and then we subclass it in the Java world. Now in the Python world, we don't have to worry about subclassing. We just have to make sure that each class responds to the same messages, right? And then, right, so our order list then has some field or property that contains that instance of the algorithm. And then we can use it to figure out where the thing, when we add something to the list, where it goes, right? So we don't need, this huge inheritance structure. We just say, okay, we need, for each way we want to order it, we have a subclass, and order list stays the same. So far, so good. So basically, the structure of the pattern is we have some sort of context that needs to use an algorithm. And my example was the ordered list. And then there is some interface that the algorithm objects have to implement. And then there's concrete strategies that implement it. And then our context has a reference to one of the concrete strategies and uses that to do whatever it needs to do. Right? So it's a very simple structure. Right? So now the problem is, right, the algorithm does some work for us, but the data the algorithm is going to use is in the context. Right? And so we've, assignment one, I beat you over the head by saying, the whole point of algorithm programming is we have a construct which holds both the data and the operations, right? And now right? The strategy pattern is going to break that by saying, okay, look, I want to be able to change some part of the behavior, and so I'm going to separate out the algorithm from the data, right? And so we're breaking this sort of the prime directive to give us flexibility, but it comes with a cost, right? And the cost is the data is over there and the operation is here, right? So how does the strategy object get the data? Um, well, it's an obvious way. One is you just pass the data it needs, right? There's a method in the strategy object, and you have an argument list, and you pass the data you need in the argument list. But then, of course, the context still needs the data, and if it's modifying the data, we need to make sure that the context gets the modified version, right? In the order list, the example is, you have to modify that list somehow, right? And make sure that the context, or I guess order list, has the reordered list. Now, one common place you see this implemented is how do you build a collection type, array list, or whatever you want to call it, that you can use to sort, keep data sorted, right? How do you do that? Well, you have a sort algorithm, right? And at some point, the sort algorithm has to compare two elements and say, this is greater than that, right? So in the sorting case, the algorithm is just, how do I compare the two elements? And so the algorithm is as simple as, is A greater than B or not? We're done, right? And then when we have our sorted collection, we have to tell it, here's how we compare two elements, right? And so in that case, right, in the Java case, the comparator becomes the algorithm, right? The concrete comparator is the concrete, and the comparator interface is the strategy interface.
And that is just the strategy sorting algorithm, not the comparator.
That depends upon whether or not you want to be able to change the sorting algorithm to be, from quicksort to merge sort or some other, or is it just how you compare the elements?
Having a sorting algorithm as the strategy example.
It's a more interesting example, but it's not the common example, right? In most languages libraries, there's a way you sort things, and you just tell it how to compare the elements. Now, IBM used to have their own version of Smalltalk, and that version of Smalltalk, yes, you could swap out not just how you compare, but the actual sorting algorithm. But that's a rare example in this case.
In that case, parameters interface with which it could resort.
Right. I mean, yeah, basically.
Give it a comparator.
Well, but in that case, what you do is say, here is our strategy interface is, what do I call on this object to sort things? So there might be a sort method, right, or an insert method. And then you would call it, and it would then, one instance of it would maybe do quick sort, one would do merge sort, maybe one would do insertion sort. Different types of sorts based upon the criteria, right? In a related example, when you got a dictionary um, or a hash table, if there are a few elements, it's actually faster just to keep the elements in a list, right? I mean, forget this table and hashing, and because if there's only 5 elements, why bother? Just it's going to be faster just to linearly search for it, and here it is. Um, so then you could have a dictionary where, depending upon the size of the dictionary, use different strategies to actually store and find the elements.
They have that. It's a hybrid.
Could be, yeah. I mean,
A lot of times it happens. So
yeah, yeah. And so it does make sense to use that spaced overhead, right? And it's even nicer if it will automatically do it for you, right? You just start off as small, then we never change. If it gets too big, then it automatically changes for us, and we don't have to think, oh, now it's too big, right? I mean, so some examples where the strategy pattern is used. Another example in Java Swing, um, when you have a GUI interface, they give you different ways to lay out the elements on the screen. And they call them layouts, right? And there's different types of layouts. Um, and that's an example of the strategy pattern because it's, comparing elements seems like a cheesy algorithm, right? It's like, that's an algorithm. Um, but they use the word algorithm loosely in the strategy pattern. But here, where you place elements on the screen, that is a complicated algorithm, right? So the flow layout is just, well, you just start and first one, second one, third one, at the end I come back, right? But there are other types of layouts. There's a grid layout, so you tell, 0, 1, 1, etc. The bag layout, which is really weird. Um, so there's different algorithms we can use to figure out where to place things on the screen. And what you do is, when you create a GUI interface, you tell it, here's the layout I want to use in this window or this container. There's an example of using the strategy pattern. And again, the issues become you have to define an interface for what operations you could do on the layout. And then you have to figure out, how does a layout get all the elements and all the data it needs to actually perform its operation and affect the context. Sort of an example, small talk. Um, when you create a sorted collection, you can give it a lambda, which tells it how to compare to the elements. And their lambdas, they use square brackets instead of curly brackets, or round parentheses, right, to define a lambda. And then they've got this crazy colon thing. Tell you the next thing is an argument. Why do we need parentheses as an argument list? But again, it's an example of the strategy pattern. And in Java, right, you give it a comparator. Now we can sort it different ways. Now, if our strategy is small enough, right, if we're just comparing things, we don't need a full object to do that, right? We can just use a lambda. And now in Java, we can do that. We can just pass in a lambda for the comparator and say, here's how I want to compare these two elements. For the layout manager, no, that's not going to work because we need a lot more data. It's more complicated. We're not going to want to implement how to arrange things on a screen in one function, right? We're going to want a bunch of functions or methods. Most of them probably private, but using a lambda is going to be too much work. So we don't need all those extra classes, right? So in Java, we can just, there's a comparator interface, but we can just say, here's a lambda. Right, so there's an example of, using a lambda in Java. Just again, we're just, they had to retrofit it so they can map a lambda will automatically map to a class which just has one function, one method, or an interface that only has one method. Yeah, so that the clients have to know about the different strategies, right? When I create my GUI interface with Sling, I have to know there's a flow layout and a bag layout and a list layout, and I have to figure out which one I want to use. I have to know about it. And then you have to figure out how the strategy and context interact with it. The strategy needs the data and has to do some work, and then has to let the context know here's the result somehow, right? And what that means depends upon what the strategy is doing and what the context needs, right? So we get rid of subclassing the context. We can just give it a different strategy. Also, sometimes you might get code with like the switch statement, right? If it's A, you do this. If it's B, you do that. Right? You've all done this, right? Okay. Depending upon what state I'm in, I want to do that or this, right? And so now we can now have the strategy object be swapped in or out and just tell the strategy, here's do your thing, right? And once patterns become popular and refactoring becomes popular, then the obvious thing is to combine the two, right? So there actually is a book called Refactoring to Patterns. And what can I say? So one of the authors of the design pattern book says when he writes code, there's only one pattern he ever used right away. The other patterns he doesn't use until the code tells him he needs it. Right? Then he'll modify his code to incorporate that pattern, which leads to, again, refactoring to patterns. Is like, so how does the code tell you that you may need the strategy pattern? And one way is you're like, okay, I want to sort by this algorithm or that algorithm. And so or you might have, in the dictionary case, maybe 3 different strategies when it's small and medium sized or very large, right? And then what you have is you start having all these case statements in different spots. If the size is less than 10, do this. If the size is between 10 and, I don't know, say 10,000, do this. And if it's greater than 10,000, do that, right? And once that case statement is in multiple places, it's like, well, yeah, that's going to be sort of ugly. So now let's refactor it to use a strategy pattern where, I have three different strategies, one for less than 10, one between 10 and 10,000, one for greater than 10,000, right?
With the strategy patterns, with that example you had, normally would you set it up so that they cast in their own strategy if they didn't
Right,
like
right.
or
Yeah. And then when you talk about refactoring your patterns, right, you want to be careful not to do massive changes of code all in one step, right? That's always a disaster. It's always painful. I'm going to go in, I'm going to make all kinds of changes, all kinds of places, and then recompile and assume things will work. Never happens, right? No. So you want to be able to do it in small steps, right? And so if you've got this case statement, you pick one of the cases, right? We want to implement a strategy that can do that case. Then we can, in that case, instead of having, we can then delegate that one case to the strategy object, right? Do the other case, we'll still have the case statement, but case statement will, instead of having the code there or call this function, we'll call a function on a strategy object, right? And then you can do that one by one to all different strategies, and then you can go through and find all the case statements and change each case statement to use the strategies and still have a case statement. And then you can start getting rid of that case statement by just saying calling a method on the strategy, right? So you want to be able to do it in smaller increments. You don't want to say, okay, I'm going to replace all the strategies, I'm going to get rid of all the case statements, and then hope it all works. The problem is you might not realize there's one other case statement over there, right? Again, you always want to be able to make these changes in smaller increments. Unless, of course, you like spending all evening, all night, working until 4 in the morning to get back to where you were. And
yeah, the worst with that is rapid, like direct access. I'm making sure run it, nothing on the screen.
yeah,
Back it off.
out, right? But if you really want to have lots of fun, don't check in the code before you start modifying it, right? And then it's like, oh, how do I backtrack, right? And then do it the day before the assignment's due or close to ship date, and then wonder why you feel stressed out at the end of the day. So eventually you want to go from there to there, right? But we don't have to do it in one step, right? We can implement a strategy and replace do a with, strategy dot do something. Um, so that's the strategy pattern. Any questions? Yeah, so the question is, you always want to get rid of case statements? Um, Not necessarily. So there's this rule of three. I mean, the first time you see it, when you have two of them, like, I don't like this, but you're a certain, no, there's three of them, like, okay, now it's gotten too bad. It all depends on the situation too, right? What's going on? So the intent of the state pattern is to alter an object's behavior when its internal state changes, right? And they say an object will appear to change its class. What they really mean is it'll change its behavior. Um, and here is the structure of the state pattern. You have a context. The context has a reference to a state object. There is a state interface or abstract class that your concrete states implements, and then the context is going to call a method on the state object. Um, I would say it's almost identical, right? Because the strategy object, you had a context, and the context had reference to a strategy object, and there was a strategy interface, and there were concrete implementations of the strategy interface, right? Which is exactly what's happening here. And this is, like I said at the beginning of the class, this is two of the patterns that the lawyer student would mesh together because the structure is the same, right? Um, so the example I use is a grader program, and there are different types of operations you want to do. You want to look up your grades. So you may want to see when things are due, right? Um, you may want to log in. You may want to then view your grades. And if you're the instructor, you may want to post grades, right? So different types of operations. Um, and the different type of operations you can do based upon the state of the program. If you're not logged in, then you can view the dates and you can log in. That's all you can do, right? You can't post grades, you can't see grades until after you've logged in. And so viewing and posting grades is not allowed, right? If you're not logged in. When you're logged in and you're a student, you view dates and you can view grades, your grades, but you can't post grades and you can't log in. Well, just assume you have to log out before you can log back in. And then if you're an instructor, you can view dates, you can view grades, right? You can post grades, you can do almost everything, but log in. Now, how do we make our program do this, right? So when you write the program, you can say, oh, if logged in, not logged in, then you can only do this. Else, if you're logged in and you're a student, then you can do that, right? So if you say view grades, then you could have this case statement. Oh, are you logged in? No, then you can't do it, right? Are you logged in as a student? Okay, you can view the grades. You want to post grades? Are you logged in? You can't do that. you're logged into the student, you can't do that, right? So each operation has an embedded case statement, right, to make sure that you were in the right state to be able to do those operations, right? And so then you get this, a huge case statement. View grades. If they're not logged in, then okay, you have to go onto the login page. If you're a student, you can show grades. If you're an instructor, you can show all the grades, right? And then all the operations start to look like this huge case statement, right? So this is, one way of solving the problem of this programming, having different operations which are valid when they're in different states. So the state pattern is obvious, right? Okay, what we're going to do is we're going to have a state object like we had a algorithm object, and the state object, when you're not logged in, is just going to say, oh, you want to view grades? Automatically go to the login page, right? You want to post grades, you're not logged in, automatically go to the login, right? And then post grades. So we can come up with different states. There's not logged in as a student, logged as an instructor, and then the parent class or interface or abstract class defines what operations we can perform. Then here's an example of doing it for the student. When you're in the greater state, what do we do? Well, when you log in, okay, but you're already logged in, so there's some error message. View grades, logging out, fetch student grades, post grades. Sorry, but maybe log this as the student is trying to do things they're not supposed to, and then display an error. In a greater program, we start off a state object, and then when we try and log in, we call the login method on the state. Again, very similar to the strategy. We have a field or property that we use to perform some or all the operations for the object, usually just some.
The example that we were talking earlier with as the size gets bigger,
right?
That's almost common. It's a state transition.
Right.
When you get over the size of the state, when you transition to the state, we're using it.
Right. Yeah.
In this pattern, we're associated. Was the state diagram for moves to this state.
That's still useful depending upon what the program's doing, right? Being able to think of your program in different states it could be in. If it has those states, then it's nice to know about it because in gaming, when we're talking about games, that happens a lot, right? Because you have different characters could be in different states. You can be alive, half alive, or dead, or you can inactive, different, right? Games can be paused or not paused, and so there's lots of different states that actually occur in a game. So I presume they still draw those state diagrams to see what can and cannot be done by different characters in the game, and different when they're in different states, and what game is in different states, right?
Yeah,
Right. Right. Yeah. You're doing different. Yeah. But again, we have some of the same issues. One is, again, we're violating the prime directive because the context probably has the data we're interested in, but the states are doing some or all the operations. And so, how do we get the two together? Um, Another issue is when we transition from one state to another, who does that transition, right? In this example, right? Um, if we're not logged in and we have a login state and it validates whether you're a user or not, um, does the state itself tell the context, here's your new state by returning the state? Or does the context say, okay, try logging in and tell me true or false? Did it really log in successfully? Oh, then I will now change my state from not logged in to logged in. An example of a dictionary, right? You probably want the context, the outer dictionary, to keep track of the size, and when the size crosses those boundaries, it will then change its state. Okay, it's time to go from linear search on an array to using a hash table. Oh, now we cross this huge boundary. It's really, really big. Now we want to use a sparse array to handle the dictionary instead of allocating this humongous table. Right. So we have to worry about who defines the trait transitions, and depending upon the situation, you may want the context to do it, like the dictionary example. Um, and we may want the states to do it. I mean, when you log in, the login object will know, okay, that's a valid login, so the next state should be this one, right? Or they logged in and they're a student, so I should return a student logged in state instead of a faculty instructor login state. Um, but then you get into this problem of, well, if the state returns a new state, then what happens if we also wanted that operation returns some actual data? And language like Java, you can only return one thing, except of course you always put it into like an array and return the array and then unpack the array. Um, right, so it's one way around returning two values is we can pass in reference to the context, and then the state can tell the context, here's your new state, and then return a new value, right? So what's happening here is, right, I pass in a reference to the context, it can call the set state, the state can call the set state method in the context, and then return some value, right? So there's various ways of having the state return, set the state, and return another value. Now, if we keep all the data in the context and the states themselves have no data, um, then we don't need multiple objects of each state, right? Because it has no data in it. So if we've got a number of objects in a program that use the same states, then we can use only one copy per version of the state. And when we talk about the singleton pattern, we'll see how we can do that. Um, Now, what's the difference between the two, right? One difference is the rate of change. Usually, with a strategy pattern, um, when you create the object, oh, I'm going to sort it this way, I'm going to sort it that way. And usually, you may not change your mind. You're like, I want all these things sorted this way. I'm done, right? Give me the list. I'll do something with it. With a state pattern, you expect the normal course of events that the state will transition. In the dictionary example, right? Um, it's normal that you start small and grow bigger, right? So expect, yeah, frequently it will change state. In the grading example I gave, yeah, you expect to start in the not logged in state, and then you go to a logged in state, one or the other, and then you go back to, right? You expect that to be a natural and occur fairly often. So one difference, even though the structure is the same, right? One difference is the rate of change. Um, it's also exposure to the change. So with the strategy pattern, right, the clients know about the change, right? I have to explicitly say, here is the layout, right? In the greater program, right, the code never has to say, oh, here's how you start. No, no, the greater program keeps track of internally, it does all the changes for you. In the dictionary example, right, it's sort of a hybrid, like you said, because it may be that you know in advance that it's going to be big, so let's just start off with this, right? But probably most of the time you don't care, right? You just start, create a dictionary, and when it grows, it automatically changes. Yeah, but this leads to what I think is one of the important things about design patterns is we're going to come across a number of patterns that have almost identical to the same structure. There's a couple famous there's lots of famous quotes, but two relevant ones are: there's no problem in computing science you can't solve by adding another level of indirection, right? Just use pointers or pointers to pointers, right? Um, and that's what we're doing here, right? They're just adding a level of indirection to give us flexibility in both cases. But then what's the difference, right? For me, what becomes the difference is, what is the problem you're trying to solve, right? What's the issue that you're trying to address? Um, and the issues here are slightly different. With a strategy pattern, just like different times when I use this class or this object, I want it to behave slightly different. I want it to do its work slightly differently, right? The state pattern is like, oh, not only do I want to do it differently, but it's going to be do differently at different times in its lifetime, and it may cycle through quite a bit, right? We yeah, 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 right. So it's solving slightly different problems. We don't think of when you're in a gaming situation, the program has different states, right? We don't think of that as, well, I just want to change the algorithm. It's like, no, I want the behavior to be different, right? You run in a way so you don't turn around and attack people, right? That's a different state, right? When the game's paused, things behave differently. We don't think of quicksort changing its behavior based upon whether I'm going to sort by the first name or last name, right? It's the same process. It's just minor little detail, but it's still sorting and it's still the same steps are going to happen right in the same order. Um, so to go through these patterns, right? You want to keep track of, you know, what what issue are they trying to solve? What problem are they trying to solve? What's their intent? Because a lot of them are going to have this exact same structure. Any questions?
But in both, one of the objectives to get this kind of polymorphic behavior out of your primary inheritance.
That's correct. Yeah, your primary inheritance tree becomes much simpler, smaller, right? Maybe not just a single object, right? Yeah. And then in a language like Java, then you have this other inheritance tree over here that allows you formal flexibility at runtime. I can actually select which one I'm going to do, right? In the dictionary case, I mean, the state pattern, you can't solve that issue with his inheritance because you have to then create a new object and grab all the state here and put it over here, right, each time. And that's complicated because then you have to worry about everything that points to that object, right? In most languages, you can't do that, so you have to be really clever and somehow keep pointers. Well, the standard solution is you keep double pointers, and then you have this one pointer to a pointer table, and in that table you point to the object, and then when you want to swap object out, you just go to this middle one and change that one pointer, but then you have to know what you're always doing with double pointers. And what? You're right, yes. Yeah, Apple used to do that all the time in behind the scenes, is they always had double pointers. Um, it made memory management easier, right? Because now you could move things around and just change that second table and not all the pointers themselves. Well, I mean, you could have a wait state, right? Or um, and that also gets more interesting because now it's not like your program has one state, right? You have a connection, and that connection is in different states, right? And you've got multiple connections going on at the same time, and that's where sharing the same state object may be useful because if you've got 1,000 connections at the same time, and there's different states they can each be in, um, and the state objects don't have any data in them, then we don't have to have 5,000 or 10,000 different objects. We can use the same one over and over again and save some space. Um, Well, this one I really liked because in Smalltalk and Lisp, you can actually change the class of an object. And of course, I actually had to try it once, and it works. But it's scary. It's really scary.
Must pass it. Well, it doesn't act.
This actually will change. It actually changes the behavior. But the scary part is, you've got fields, right? And the two classes have different list of fields and how they get mapped. And you have to be very careful with that because they're in Smalltalk they're mapped by position. And so when no, you can literally change class. Yes, the fields always match until you try and use them. Well, actually, I mean, all you do is you take those. The first field becomes the first field over here, right? Um, and so when you call a method on the first field, if it's the right type, you're in good shape. But, so when you write those two classes, you have to make sure that each field position is the right one, right type. And I tried it as an experiment, and I realized I really don't want to do that. I'm sure. I'm sure there are a few rare cases where it's what you want to do, but they'd be very rare. But it's interesting to know that you can actually do that, right? And oh, what's this all about? Um, yeah, so there's another alternative to the state pattern, and perhaps the strategy pattern. But to understand them, we have to understand single dispatch and multiple dispatch. Um, so here, in Java, we have what we call single dispatch. So I have a parent class and a child class, right? And there's, um, I don't need any behavior there, so I didn't put anything to keep the example fit in one slide. And now I've got a bar class, and it has two methods, both foo, but one has a parent parameter argument and one's a child argument, right? And that's allowed in Java because the the signature of a method determines whether it's unique or not, and the argument list is part of the signature, right? Um, and now, when I create a bar object, I create a new parent object and I call foo on it. I get parrot, right? But now when I assign a child object to x and I call foo with x in it, I still get parent. Why? Because the compiler is the one in Java that matches which function is going to be called based upon the argument list. And the declared type of x is parent, so this foo is going to always call the right, and it's not going to look at the actual type of the object of x to figure out which one to call. Now, when I define a new variable of type y and pass it in, right, the compiler is going to look at the declared type of y and it says child, so it's going to call that foo. And so I will get child, right? And so it's single dispatch. Why? Because It only worries about the receiver, right? If I had a subclass of bar, right, and define those methods differently in the subclass of bar, and it changed what test was, then at runtime we'd figure out which class to use, right? But that only gives us one change at runtime, right? The receiver. At runtime, we'll look at the receiver,